Okay. So to continue with the summary, so we look at expectation of random variables, right? So before that, we already look at random variables, okay, what they actually are. Okay, random variables as set functions, yeah. And then we want to find their expectation, which is given in terms of the Lebesgue integral. Okay, so this is a little bit different from. So this is your Lebesgue integral, right? And of course, when you studied in the first year and all that, you might have come across, like, for example, this is the Riemann integral, okay? And so this is for discrete case, right? This is for your continuous case, right? But your Lebesgue integral is completely general, right? Okay, so your Lebesgue integral will be completely general and handle both cases. Okay. Now from this definition of the expectation of x, so of course this means that if you have any kind sort of function, right, of x, then it basically is just, okay. So this is the function and this is the measure, right? This is the measure of the function of gx. Okay, this is the probability measure. Okay, then we have, from here we have two results, yeah. For non-negative x. So for non-negative x, your expectation of x can be written as the following. Okay, is the integral of the tail probability, right? And this is for if your x is continuous, and if it is discrete, it will be, the integral will change to summation, yeah. Okay, the sum of the again is the sum of the tail probabilities, right? Okay, so these are more for theoretical theoretical settings. Okay, for computation, sometimes they are easier than the use of standard methods. Yeah, sometimes the standard method is easier. Okay, but it's nice to know that there are alternatives to calculating the expectations of x. Okay, so after the expectation, we have the concept of independence, right? So this is really just a short section, and we wanted to just make sure that when you say that, so suppose you have events. Okay, so if you say that they are all independent, this means that First, of course, their intersection must be equal to the product, right? And then also it has to be all the other combinations. For example, A1, A2 must be equal to the product, and same with the other combinations, yeah. Okay, so there will be here, there will be, you have n choose 2 pairs, right? Okay, so, and then so on and so forth, right? Okay, so then you have PA1, 2, 3. They all have to be A1, A2, A3, right? The product. Okay, so all of them, so there will be n choose 3 things to check here. So altogether, you basically, when you say that they're independent, it means that all these conditions are true, yeah? So you cannot just simply check one of these conditions or maybe just this condition, but the other conditions are not true. When you say that they're independent, it means that all these are true, yeah? Okay? Okay, so that's just a short section on independence. And then we have the Borel-Cantelli lemmas, right? So, okay, we have the first and the second. Okay, so basically this are just theoretical results, and especially the first Borel-Cantelli lemma is used in the proof of the strong law of large numbers. Okay, so so you have the first Borel-Cantelli lemma. Okay, so basically you have A1, A2, and everything in F. And if the sum of if the sum of all these events is convergent, then P lim sup an is equal to 0. Okay. All right, and this one is actually used in the proof of the strong law of large numbers, right? Strong law of large numbers. Okay, so let's look at the second Borel-Cantelli lemma. So right here. Okay, second Borel-Cantelli lemma makes certain assumptions about your sets of A's. So if A1, A2, if all of them are independent, yeah. Okay, and the sum is divergent, right? Then you get the converse, right? P lim sup an is equal to 1, right? So you can see that these two lemmas, they are basically kind of like opposite of each other. Okay, so this one, if it's convergent, then you get this result. This one is, if it's divergent, you get this result. But the condition there's an additional condition here for the second Borel-Cantelli lemma. Okay, so the condition is that they have to be independent, right? A1, A2, and so on. And we previously looked at this operation lim sup, right? So lim sup, you need to know the definition, right? So the lim sup of AN is union intersection, right? It's basically just a set operation, okay? And the related one is the lim inf, which is you take intersection first, and then you take union, right? Okay. So when we write lim sup lim inf, it basically means this kind of set operations. Okay, so once we are done with the Borel-Cantelli lemmas, we have the topic of convergence. Okay, where we studied three types of convergence mode, right? The first one is convergence with probability 1, right? Also called almost sure convergence. Okay. The second type is called convergence in probability. The third type is called convergence in distribution. Okay. So the first type of convergence implies the second type, and this one implies the third type. Okay. So in terms of technically, when you write this, this is written as let me see. Well, sometimes this will be written as infinitely often. Okay. Okay, so these are basically just equivalent ways of writing. Okay. This one means IO means infinitely often. Yeah. Okay. Basically, this is saying that the chance that your xn, right, this random variable which depends on n, escape from its mean, yeah, by more than an arbitrary amount, epsilon, infinitely often. Okay. That means it can escape from epsilon, but it escapes from it only infinitely many times. Okay. The chance of that happening is 0. Okay. So that means it can only escape. It can only escape from the mean only a finite number of times. Okay. So this one, this result basically we only use it for the strong law of large numbers. All right. Inside because strong law of large numbers is basically convergence with probability 1. Okay. So we only use it to support that case, right? The rest of them we basically just look at convergence in probability and convergence in distribution. So convergence probability is the following. So we basically say that the limit of this probability equals to 0, okay? Which basically says that in the limit, your xn, yeah, cannot escape from mu by more than a certain amount, right? That chance is impossible. It cannot escape, okay? So this is called convergence in probability, right? So this provides a kind of an idea of closeness, okay? Because in the limit, we want our xn to be close to our mu, right? So when you say close, right, you have to define certain sense, okay? What does it mean to be close, all right? So the meaning of closeness here is defined in terms of defined probabilistically, right? Which is saying that, okay, it is saying that we say that it is close, right? In the sense of convergence in probability. If this, if your xn, right, doesn't get away from mu by more than a certain amount, right? Right, getting away from it by more than a certain amount in the limit is impossible. Okay, so this is the idea of closeness. Then you have convergence in distribution, which basically is just the if you have fnx is the CDF, right? Cumulative distribution function of xn. Then you have basically limit, okay, equals to fx. Okay, so basically this one is just saying that the distribution function of xn becomes the distribution function of in the limit, yeah, it becomes something, okay? And this one, since this fn, right, is an integral, isn't it? Okay, so you have maybe some, okay, you maybe have some integral like this. So then you take limit, right? So all the things that you studied previously, like the Lebesgue dominated convergence theorem, right, will be useful in the case that this fn, right, is in the form of an integral, right? Sometimes your distribution function can be expressed in as a closed form, right, as a function. But sometimes it cannot be expressed in a closed form, right? Sometimes it just is in the form of an integral. So if you want to show convergence in distribution, then you can use Lebesgue DCT, right? Just establish domination, right? Some domination of this function, and then you can interchange the order of taking limit and integration, okay? So these are the three things that we learn for convergence. And after that, we learned a bit about inequalities for probability work, right? So these are the inequalities that are important in probability work. So the first one, we learned about the Markov's inequality. Okay, Markov's inequality is given as follows. So okay, so the probability that the absolute of x exceeds some positive constant, yeah, alpha, is bounded by its the kth moment of its absolute, okay, and over alpha power of k, right? So you can basically this form is very useful because you can basically choose your k, right? And in fact, Markov's inequality was used in the strong law of large numbers, okay, for the proof. And it can also prove your Chebyshev's inequality. Okay, so this inequality is really useful. The second one is the Chebyshev. Okay, basically, so this is bounded by the variance of x over alpha square. Okay. This is basically just your Markov inequality. With k equals to 2 and x equals to the centered form, right? And we basically use for proving convergence in probability. Okay, it's mainly used for proving this result. All right. And then there's another inequality. Cantellis. Okay, Cantellis inequality. There are two forms. This is the one-sided. Okay, this is the one-sided Cantelli. And the other is the two-sided. Okay. The two-sided, basically you add the absolute and then you add a 2. Okay, sorry for the interruption. I'm having a bit of a flu now, so okay. Okay, then the fourth inequality is Jensen's. Okay, Jensen's inequality. So basically for this one, you have the following. Okay, if your F is convex, okay, so then you will reverse the sign. Yeah? If F is concave, right? Okay, so it's actually quite easy to use. Basically, you just need to determine whether your function here is convex or concave, right? So convex functions are like this, okay? This is an example of convex functions. Concave functions, they go in the opposite direction. Okay, so an easy way to remember convex and concave function is that you see the word cave, concave, right, has the word cave, right? So this looks like the entrance of a cave, right? So this is how you kind of like remember easily how generally the shape of convex and concave functions look like. Okay. All right. So for example, this is very useful, right? So an example here would be suppose so. If you have fx1 over x, right, this is is it concave or convex?
Convex.
Convex, right? Because okay, you see, if it convex, right? If you put a secant line through it, right? The secant line will sit on top of this. So this is your secant line, right? The secant line will sit on top of the curve, yeah. The concave, right? You put a secant line. The function, right, will sit on top of your secant line. Okay, so it's very easy to determine. Yeah? After you sketch, just put a secant line, see whether a secant line is on top or below the curve, right? So this is convex. And therefore, if you apply this inequality, immediately you will get 1 over expectation of x is bounded by expectation of 1 over x. Okay? Right? So you know that very quickly, if you know the expectation of x, and now you are interested to find the expectation of 1 over x, right? Then you can use Jensen's inequality to at least get some idea about its bound, right? In this case, you'll get a lower bound for expectation of 1 over x, okay? So it's very convenient. You can think of other other functions like log. Log is common. Exponential is common. In fact, if you use exponential, right? So exponential function is convex or concave? Convex, right? Okay. Exponential function, your secant line is sitting on top of the curve, okay, between these 2 points. So then you can apply this inequality. So you will have exponential of, let's say so a very interesting part will be the moment generating function, right? So your moment generating function is e of e tx, right? So it will be this one. So since it is convex, right? Exponential function is convex, so it will be larger than or equals to e of t of expectation of x, which is e of t mu. Okay. So you know that in general, your moment generating function, right, is larger than or equals to the expectation of t times mu, yeah, the mean. Okay. Right. So so this is Jensen's inequality, and then the last inequality that we learned was Schwartz inequality. Schwartz inequality. Okay. So Schwartz inequality gives the following, yeah, the expectation of absolute of xy, okay, is bounded by the square root of expectation of x squared and expectation of y squared, okay? So from here, you can basically, so sometimes you can actually basically choose your y, right, to be of certain form. Okay, so for example, if you choose your y to be equal to 1 over x, then you will have, so x times 1 over x, you get 1, right? It becomes a constant. Then this is bounded by expectation of x squared, okay, and expectation of 1 over x squared, okay? And this one you rearrange, you will get, you take square and then rearrange, you will get 1 over expectation of 1 over x squared is bounded by expectation of x squared. Okay, And basically, this is just Jensen's inequality, right? For f equals to 1 over x squared. Right, so sometimes, so there's a connection between Schwartz inequality and Jensen's. For certain cases, your Schwartz inequality will be actually the same as your Jensen's inequality. Okay, so either using either one of these inequalities will be leading you to the same result. But otherwise, your x need not be a function of your y need not be a function of x, and so you can if you have separate functions, then you can basically just find such things like separate. Your y can be a function of x, but it need not be a function of x. Right? So this is actually more general. Okay. So then, once those tools are available, then that allows us to study the limit theorems, right? So we basically studied 3 limit theorems. The first one was the law of large numbers. You got the strong and the weak version. The second one, there was the central limit theorem. And the third one was the law of iterated logarithm. Okay, so the law of large numbers concerns the convergence of this quantity. So let's say you have, so suppose you have x1, x2, xn being ID, right? Independent and identically distributed random variables. Okay, let's say suppose for simplicity we will say mean is 0 and variance is 1, right? We scale your scale the random variable so that they have mean 0, variance 1. Okay, to ease the discussion. But of course, in general, they can be mean of mu and variance something else, right? But you can always scale them, right? Subtract the mean and divide by the standard deviation, and then you will get this quantity. Okay. Now, the strong law of large numbers concerns the convergence of this thing, this quantity, where your Sn, right, is the sum, right? Okay, sum of the NID random variables. So your Sn over n is basically your sample mean, right? So basically your limit theorems concerns the convergence, right, of of the forms of Sn. Okay, now over n, square of n, and okay. So the first one, law of large numbers, concerns the convergence of your sample mean actually, which is the sum divided by just n, yeah. This one is shown to be converging almost surely, okay, to 0, right, to the mean, yeah, the mean is 0. So it converges almost surely, which is actually convergence with probability 1, yeah. Okay, that's the strong law. The weak law is convergence in probability to 0, okay? It's convergence with probability to 0, right? So these are the two, this is essentially what is just trying to say, right? Convergence almost sure, and convergence in probability, okay, of Sn over n. Now the central limit theorem concerns the convergence of the following form. Now, of course, you will start out with the sample mean, right? Okay. You subtract the mean, which is 0, then divide by the standard deviation, which is 1 over square root of the standard deviation of Sn over n, yeah? So it'll be this thing, and end up you will get Sn over square root of n, okay? So now instead of having the denominator as n, you have a square root of n, okay? And what can we say about the convergence? So this one, the CLT gives you the convergence in distribution, yeah, to normal 0, 1, okay? So this is a universal result, regardless of the actual distribution of your x, yeah? Your x can have any funny distribution, as long as they have finite mean and finite variance. Finite mean, finite variance, it doesn't matter what is the actual distribution of your x, okay? In the limit, okay, in this case, your Sn over square root of n will converge in distribution to the standard normal, right? So this is a very powerful result because it basically allows you to construct statistical properties, right, of the sample mean, regardless of the underlying distribution, yeah. So because they are from these different distributions, sometimes you might work with skewed distributions, okay, bimodal distributions or whatever, and you're interested in the mean, right? So this central limit theorem guarantees that if your sample size is large enough, then your sample mean is basically normally distributed, okay? So then you can use your 95% confidence interval calculated from the normal distribution. Right? So this kind of like unifies the results, okay? So you don't have to have a separate result for each and every different distribution, right? So that is actually, no one can handle this situation, okay? There's just simply too many things. But this one is basically I just put everyone together, yeah? So the result is that this result concerns the Sn over square root of n, right? The convergence. But it is basically saying a convergence in distribution. Now the law of iterated logarithm basically concerns this result. 2n log n, okay? Log, this means you log of log n, yeah? This one converges almost surely to 0, yeah? Okay? So, okay. So, okay. Right, okay. So this law of iterated logarithm concerns the convergence, right, of the Sn, right? But with the denominator given by this form. Now, if you look at the denominator, look at these three denominators, right? Which one is the largest? Which of these three denominators is the largest? We just rank the three denominators. Which one is actually very easy to rank them, right? So which one is the largest? N square root of n and this one. Anyone wants to answer this?
N.
Sorry?
N is the largest.
Okay, then the next one.
Then is square root n.
You are saying that.
Oh,
You're going like this. Are you saying this?
yeah.
Why do you say so? Okay, this is clear that this one is the largest, right? Because you take square root of n, then it will be smaller, right? But why do you think this one is larger than this one? Why? Isn't the other way around? This should be larger than square root of n, right? Right? There are three parts here, right? So this part is definitely larger than 1, isn't it? So therefore, this thing should be larger than square root of n, okay? So it should be the other way around, yeah? So your n is here, your your log n is here, and then your square root of n is here, right? So basically, the limit theorem, for the limit theorems, you basically, what we have learned is that we have, so this result concerns the law of large numbers, right? Law of large numbers. Then the square root is basically the CLT. CLT is here. Your law of iterated logarithm is sitting in the middle. Okay. Regarding the behavior of Sn with different denominators, right? This one is talking about the denominator is n. This one talking about denominator is square root of n. This one talking about the denominator when the of 2n log n. Okay, and all of these they converge to 0, right? But they have different modes of convergence. This one is almost sure, and converges in probability. Okay, this one is almost sure. Okay, and this one is in distribution. All right. So this is the basic result that kind of like links them together. Okay. So in practice, we just need to know this structure, and then then the rest is basically just applications, right? So for some fine details like your central limit theorem, we have two conditions, right? The Lyapunov and the Lindeberg. Okay, so So the Lyapunov and Lindeberg conditions are the ones that you check. Basically, if this, you can check either one, right? Either one will do. As long as you can confirm that the Lyapunov condition is satisfied or the Lindeberg condition is satisfied, then central limit theorem will hold. Okay. Previously, you kind of like you basically just apply it, right? But now you have some additional tools to kind of like check it. Okay. Okay. So law of iterated logarithm is just put in there for you to. It's basically not much use now. But then just to complete the picture, yeah. So just to let you know, right, there is some results sitting in the middle between CLT and LLN. All right, okay. So that's your limit theorems. And the last part is your characteristic function. Okay, so basically your characteristic function is just it exists, yeah, for all distributions. Okay, because your EITX is bounded, right? Okay, because this is a complex number, yeah. So EITX you have in characteristic function we use De Moivre's theorem, De Moivre's formula a lot, right? De Moivre's formula is E of I x cos x plus I sine x, right? So this part is called the real part. This part is called the imaginary part, okay? So basically you can, so here you can basically replace your x with whatever, right? So then you will make up replacements similarly here. Okay, clearly this is bounded because the absolute of this thing is equal to the square root of this term, yeah, plus the square of this term. Okay, so this is 1, right? So it's bounded. Okay, unlike your moment-generating function, your moment-generating function is just E of Tx, right? Is basically unbounded. Okay, so you will have situations where your MGF does not exist. Does not exist for certain distributions. Such as the Cauchy, right? The classic case where it doesn't exist. Okay, so now characteristic function, it exists for all distributions. And then the other thing is unique characterization. Okay, that means it's like a barcode, all right? If you find that there is actually a random variable, okay, you find it's so maybe certain transformations or whatever, then you'll find its characteristic function. And if it matches some characteristic function of already some known distribution, then you know that the transformation has the same distribution as the one, right, that has the same CF. Okay, so that in that sense we have something called unique characterization. So it's very useful, right? It's just like an identity tag, okay, for the distributions. So working with CFs, first thing, of course, we have trying to find it, right? Find this one, right? So basically it is, so we need to evaluate, okay, this one for continuous, right? Then of course for discrete, you will have this, okay? Okay, so generally, if you want to evaluate using the definition, right? So this is basically, strictly speaking, this is a complex integration. So we never learn how to do this, right? But then that's why in certain cases like this, if you just try to use, okay, we may actually try to hack it using by pretending that this is a real integration, right? But you pretend that I is pretend, okay? You pretend is a real constant, and you work through it with the standard machinery or real integration. You actually will get the same result, okay, as if you had used the complex integration. But it's actually just a hack, right? So there will be some cases where you will not be able to push it, all right? So most of the time, what happens is that if you know the MGF, okay, you do the MGF, and then because MGF, of course, you're using the real integration, right? Then you basically, after that, you replace the T with IT. Okay, so that will give you the CF, right? But of course, this will not work with the Cauchy, right? Because the Cauchy will, it doesn't exist, right? Okay, so you can't use this technique. But otherwise, for other distributions where your MGF exists, you can basically just replace the T with IT. It'll be the same, okay? And then finding that, and then you have the finding a moment, right? So finding moments will be you differentiate it k times and divide by I power of k, so that will be your moment. Okay, your k moment, right? So basically, it's almost the same as your MGF, right? MGF is also you differentiate. So your moment generating function, you basically differentiate the MGF k times, and then you set to 0, right? You also get this. Okay. The difference is that it has a denominator. You have to divide it with I power of k. Okay, for characteristic function. And then the other thing is the inversion formula. Okay, so which means if given CF, find the fx, all right? So this one for continuous case, so my fx is equal to 1 over 2 pi of this thing. Fx. Okay, so sorry, this is the phi. This is the characteristic function. Okay, phi, this is phi t. Phi t dt. Okay. Okay. So again, strictly speaking, this is a complex integration, but you can pretend that the I is a constant, real constant, and then try out the real integration machinery, right? So inversion formula can help you recover the fx. Okay. And there's a last one where you can also calculate probabilities, yeah, using CF. Okay, so you basically have a result like this. So okay, this is like a probability of x between a. Doesn't really matter if if it's continuous, then it doesn't really matter if it's like open close, right? So 1 over 2 pi of this thing minus b over I t, and this part is the phi t. It's actually a minus. Okay, so so except for, so as you can see, since this involves a complex integration, it will be a bit difficult to do, all right, unless you know complex integration. But most of the time, we may actually use this to find bounds, right? We can use it to find bounds for mu AB, right? Because we know that this is definitely bounded by the absolute form. Okay, so definitely bounded by this thing. Okay, then depending on, so then you can simplify this part to have a real and an imaginary part, and then you can find its absolute, okay? So then you can basically bound, once you find a suitable bound, you can continue to bound it until you get some integral where you can actually evaluate, right? And then you can find an upper bound. Okay, so that may be one use, okay, of this result. And here again, your de Moivre's formula will be important because when you use de Moivre's formula, you can frequently simplify this part, right? Simplify until it is left with the sine and cosine terms. Okay, so please remember your de Moivre's formula. Okay, very important when you work with complex functions. Okay, so basically those are the things that we studied in this course. All right. So do you have any questions regarding this summary here? Okay, so this gives you a structure of what are the things that you have learned, yeah, the summary. Okay, okay so I will take a 5-minute break, right? I'll come back at 12:10, and then we will start with the last tutorial. I think are you muted? Why can you turn on? We cannot hear you speak. Okay, your mic is not functioning. Never mind. Share the screen and we just go through it and just comment on it. Okay. All right. Okay. Okay. So you just state down the Lindeberg condition. The Lindeberg condition is that the truncated second moment, right, of the centered variable is in the limit it tends to 0, right? So okay. The first line is okay. And the second line basically, okay, so basically the condition absolute x minus 1. Actually, actually since if there's no confusion, you can just press the subscript of 1, right? That's also fine. Okay, so the lower limit of integration, right? So you're integrating from 1 plus epsilon square root of n, right? And the other one you're integrating until 1 minus square root of that, okay? So then you write, okay, then the third line, I think you left out the exponential function. What happened? In the exponential function should be there, yeah? Okay, and somehow you kind of like removed it, okay? The third line, the exponential function is still there. So, okay, so the two integrals, the limit of integration is correct, right? And then when you take limit to infinity for n, the lower limit of integration becomes infinity, right, for the first integral. So since your upper and lower limit of integration is the same, so of course the integral will go to 0. And then for the second integral, because your upper limit of integration, right, is going to negative infinity, right? So basically you're integrating a function in the interval from minus infinity to 0. And this one is actually, the function is actually equal to 0, right? Because you notice that you have an indicator function there, x has to be positive, right? So outside of positive x, basically your function is 0, right? So basically you're integrating 0 there. So of course, then you get the 0, right? So 0 plus 0, you get 0, okay? Okay, right. So, okay, for Lindeberg. So if you check Lyapunov, so Lyapunov, basically you just need to check that the, so you usually will take delta equal to 2, okay? So that that's the smallest delta that will give you an even function. Sorry, yeah, sorry, an even power, okay? So, okay, that's the condition. And basically you don't need to worry about those parts with the n, because that part will have a denominator of n. So you basically just need to make sure that your fourth moment, right, the fourth centered moment is finite, okay? So then, okay, you go down. Okay, so yeah, okay. This one is something like I show in lecture, but actually your okay, so you're split in 3 parts, right? Actually, the first part and the third part you can combine together. So that means you integrate from 0 to 2. Because within this interval, right? Within this interval, your x1 minus 1, okay, will be less than 1, okay? So basically, then you can bound it with, okay? So you can try that. And then the second part, okay? The second part, your x1 minus 1 raised to the power of 4 will be bounded by x1 power of 4, okay? Because your x1 is actually not subtracting anything, right? So yeah, it will be larger. So then bounded by that, and then it will be further bounded by, you let the lower limit of integration go to 0, right? Because then you have additional things. The reason why you do this is because you will notice that the integrand there, right, is actually something, it's like your gamma probability density function, okay? Your gamma probability density function with alpha equals to 5, okay? So then alpha equals to 5 and beta equals to 1. So basically, it will integrate to gamma 5. Yeah, gamma 5 is 4 factorial, so you get 24. Okay, so yeah, that's the whole idea to show that the moment is finite. Okay, and to show this, if you had tried to use direct integration, maybe a little bit tedious. Yeah, so use the idea of inequalities. Okay, use because you just want to show that it's finite. So as long as I can show that it has a bound, right? Then it's done already. Okay, so this is the idea. Okay. Okay, thank you. We can. Okay, the second presenter.
Doctor, can you see my screen? Not yet.
No, not yet.
Wait, Now?
Yes.
Okay. For question number 2, so we let x be a geometric random variable with parameter p, then we need to find the characteristic function of x. So we find the characteristic function by expectation of EITX, then summation of x equal to 0 to infinity, e to the power ITX, 1 minus p to the power of x times p. And then we factorize p outside of the summation, and then we solve the geometric series. Then we get p over 1 minus p e to the power it.
Yeah.
And then we need to find the mean and variance using the characteristic function. So first we need to differentiate the characteristic function. Then we get the I times 1 minus p times p EIT over 1 minus p EIT squared. And then the first derivative, we to the t, then we get 1 I times 1 minus p over p. So then expectation Ix equal to 5.0, and then the expectation x, we get the mean is 1 minus p over p. And then we differentiate again the first derivative of phi t, and then we get this, the solution. And then we substitute the 0, then we get p squared minus p minus 2, p minus 1 squared over p squared. And then for the expectation Ex squared, we get negative p squared minus p minus 2p minus 1 squared over p squared. And then for the variance, we need to use Ex squared minus mean squared. And then we solve the calculation, and then we get 1 minus p over p squared for the variance.
Okay.
That's all.
Yeah. Okay. Can you move up to a bit up. How did you define your geometric random variable? Okay. Okay.
This one?
Yeah. Okay. So you are okay because the geometric random variable has two forms. Yeah. One is starting from 0.
1. 0
Yeah.
and 1.
Yeah. The other one is starting from 1.
Yes.
I mean, like they are the same thing, but they are starting at 0. They're slightly different, lah.
Yep.
Yeah. So yours, I think your case is starting from
0.
some students may start from 1.
Yep.
So if they start from 1, they will get slightly different result. They will get the mean as 1 over p, and then they will get their variance. The variance you will get the same thing, but the mean they will start at 1 over p.
Yep. Yes.
So just to I mean, like either one is okay lah. This one is just depending on if you want to use geometric distribution as a model, then you will have to think about whether your range of values cover 0, okay, or they start from 1, right? So they are slightly more. They're still called geometric because the PMF has a geometric form, right? So, but then starting from slightly different values of x, so you get slightly different kind of I mean, like slightly kind of different mean. The variance is the same.
Okay.
Okay, thank you.
All right.
Doctor, can you see my screen?
Yeah.
Okay, so for number 3, let x be uniform random variable with interval -1, -half to half, and then find its characteristic function and its mean and variance using phi, and then verify using the standard method. So first, the PDF of x is equals to 1. So next we find its characteristic function, EITX, and then equals to here, the integral of here. And then I use from alpha to solve this complex integral, and I got this answer. And then the final answer of our characteristic function is 2 over t sine t over 2. Next, we find the mean using characteristic function. So first we differentiate the characteristic function here, and I got this answer. And then to find its mean, we have to substitute t equals to 0 in this derivative. So at t equals to 0, phi prime 0 is undefined. So we take its limit. From here we take its limit, and since this is in indeterminate form, so we apply the L'Hopital's rule for here, here, and here. And then here the fraction is no longer in indeterminate form, so we can just substitute t with 0, and the final answer is 0. So hence the expected value of x is equals to the first derivative of characteristic function at t equals to 0 over I. So here we got the mean equals to 0. Next, for variance, we perform the second derivative from this first derivative, and then this is the answer. And also at t equals to 0, phi double prime 0 is undefined. So we take the limit also. And here is the indeterminate form. So I apply the L'Hopital's rule again here in these steps. And then here is not in the indeterminate form. So we can substitute t with 0, and we got -1 over 12. So our expected of x squared is equals to phi double prime 0 over I squared, which is equals to 1 over 12. So to obtain variance, I forgot to write here. To obtain the variance is the EX square minus square of mean. So here we got our EX square is 1 over 12 and our mean is 0. So our variance is 1 over 12. So then I verify using the standard method. So our mean is equals to 0 and also our variance is equals to 1 over 12. So hence, by using the characteristic function, we can obtain the values of mean and variance same as the standard method.
Yeah, okay. Can you move up to the earlier part? Okay, a bit further up. Okay. Okay, just want to look at the integral. Okay, I'll just do some annotation here. Okay. Then actually over here, wouldn't it be, you don't need to use Wolfram alpha to do this, right?
Mm.
In fact, this is just EIT x over IT. I mean, as I mentioned, although this is a complex integral, but you can pretend that the I is a real constant and then, use the machinery of the real integration, okay? You will get the same result. Right? So then you basically just put in here and you will get E of IT over 2 minus IT over 2 over IT, right? So over here, there are several interesting representations. So this is one of the representation. One representation, so I will show several representations. The first one is, if you look at this, this becomes the hyperbolic sign of IT over IT. And basically this is equal to, if you multiply with II, then you will minus I hyperbolic sign, okay, over T, all right? This is one representation. The other representation is if you use over here, right? So if the other representation is if you use the Moivre's formula, okay, which is this thing, the Moivre's formula, okay? So basically over here you will have cos T over 2 plus I sine T over 2 minus cos minus T over 2 plus I of sine minus T over 2, okay? The minus sign goes together with the T. So your cos function, your cosine is an even function, your sine is an odd function, right? So cos of negative is basically just cos without negative. So the cos here and cos here will cancel, okay? So they are left with this part. So you have actually 2I sine of T over 2, right? Okay. So then you then basically divide. So then after that you have 2. Okay, I can write out the I here, 2 sine T over 2 divide by IT. So the 2I will cancel. So you get 2 sine. So you get this. Okay, the same thing. So that's why I am not sure your step here. Your step here is actually not. It's a bit strange to me because you mentioned that you use Wolfram alpha.
Yeah.
Okay. Well, it cancels off and then you get this, but I think you should only use, okay, Wolfram Alpha is good for checking the results, all right? And also maybe if you are trying to deal with some rather complicated formula, but in general, in this course, I would expect you to work out the integrals by hand, yeah?
Mm-hmm.
Okay, so that you understand the things that are going on. I mean, you can use Wolfram Alpha to check your result. Okay, unless the integral is very complicated, then but I don't give complicated integrals. Okay, so yeah, so these steps I think you can fill in this from here. You can come to these two steps. Yeah.
Okay.
So okay now. Then okay, can you move down? Clear this. Okay. Okay, so this is the derivative. If you had used this form, is it easier? I just want to check, yeah. If you differentiate this, you will get cos IT times I minus sin IT over T. So then this will be, okay, so this will be I cos IT minus sin IT. Okay. Yeah, so you still have to, so this will be minus cos T minus I of sin IT over T. Yeah, okay, so it doesn't make it, when you take limit, so you still have to take limit t tends to infinity, tends to 0. So this one will give you 1 minus 1 over 2. Yeah, okay. So well, I'm just wondering, it doesn't make it any simpler. So you can use this form. Okay. So yeah, then you'll take this, all right? Because you cannot directly substitute, so you take limit and apply L'Hopital's rule, so you get this, right? So this one, I'm just wondering if there's a simpler way to do it. Can you, just now, what did we get for phi t? 2 sine t over 2. Okay. So can I try to express this in terms of phi t? So let's see. So this can be written as so cos t over 2 over t minus 2 sine t over 2 over t times 1 over t, right? So this part here is your phi t. Let me see this part here. Let me try. So this will be t phi t equals to 2 sine t over 2. If you differentiate, you'll get t plus this equals to 2 cos t over 2 times 1 over 2. You cancel this, right? So your cos t over 2 is actually this thing, right? So cos t over 2 over t will be equal to phi t plus phi t over t, right? So the other way to represent your result here will be phi t first derivative equals to this thing, yeah, phi t plus minus phi t over t. Okay, well, doesn't work. Okay, let me see. So basically, it may be simpler to do if you, maybe I'm just thinking. So this will be
IT over T.
phi t over t, right? Maybe this will help you do the second part, because if you do second part, right, if you already have this result, then it's kind of easier, right? So you do this derivative, that will be t squared minus sine t over 2 times 1 over t minus cos t over 2 times that. Then you differentiate this side is t squared, so you have t this minus phi t differentiate 1, right? So then when you try to substitute, it may be easier. I'm just suggesting this because a lot of times, if you express your derivative in some form of some function of the phi t, usually the when you take the derivative, right, subsequently it may be easier. Okay.
Okay.
So, but it's not always you will get that, but sometimes it will simplify, right? In this case, maybe not much effect, I guess. But it's a useful technique to know, yeah.
Okay.
Okay, thank you, Dina.
Okay, thank you, Doctor.
Can you see my screen?
Yes.
I'm doing question 4. So this is question 4, and given x is from normal distribution with mean mu and variance sigma square. So question asks us to state the moment generating function. So this is the moment generating function. By replacing the t with it, we are getting the characteristic function to be this. And questions say that if x1 and x2 are IID as x, hence we could say that the characteristic function of x1 and x2 to be both of these. And question asks to look for the distribution of x1 minus x2 over 2. So we are going to so we are going to look for the characteristic function of x1 minus x2 over 2, and we compare to the existing distribution. So this is how I do, and end up I'm getting, because they are independent, so I can separate them, and end up I'm getting this as my characteristic function. And I'm stuck here because I couldn't find any distribution having a characteristic function. I don't know whether is it my concept got problem or what.
Okay, I think the problem is here. Here, right, you have expectation of e of I t x1 times e of minus I t x 2 over 2, right? Okay. So here you already found that you can separate out like this, right?
Yeah.
So this one you already, so you think of this 2 as together with this. Okay. So what do you get? E of I mu t over 2 lah, right?
Yeah.
What was that? Minus sigma square t square over 2 times 2 square lah, right?
Yeah.
And the other one is e of minus I mu t over 2 minus sigma square t square 2 times 2 square, right?
Yeah. Yeah.
Yeah, because your minus t over, I mean like here you group your minus, so here minus t over.
Shouldn't that become a minus mu plus sigma square? Because
Yeah, there's a minus here.
then what about the minus in the middle at here?
Yeah, this okay. Sigma square t square over 2. You replace this with minus t over 2, right?
Oh, we can use minus. We can use minus t over 2, is it?
Well, clearly here it is minus t over 2. Right?
Okay.
Yeah, you replace this generic t with this minus t over 2, so you will get the same thing because it's a square. The sign here is still negative, right? This negative sign basically is a consequence of your I square, right? Okay, so then, of course, since this and this are the same, so they cancel. But then you will get here is minus. So this is 2 t square. Then you have what? Sigma square. What do you get here? 4. You just get this, right? Times. You get 4, right? Okay. This is 4 times 2. This is 8. This is 8. So you double it, you get 1/4, right? So basically over here you have e of minus t square over 2 times sigma square over 2, right? All right. All right.
So this is normal with mean equal to 0 and.
Yeah. So once you have this, then basically this is still identical to this form, right? So now you know that your mu is 0, and then your new variance, right? This is a new variance. Is the previous variance divided by 2. Okay, from matching lah. You just matching it up and then checking. Now, so okay, so this is what you get from using CF, right? Let's check with the theory. So the theory, if you have x1 minus x2 over 2, this is still normal, right? The difference of 2 normal is still normal, okay? with the mean equal to 0, right? Because the take expectation of this is 0. You take the variance is x1 minus x2 over 2. So this is independent, so this will be 1 over 4 sigma square plus sigma square, right? So it will be sigma square over 2 lah. Okay, which is this one. All right. Okay, is it clear to you?
Yeah.
I think the part that I think what, I don't know, like what happened here. Because this part here, since they are independent, you can split out, you can write as a product like this, and then you can simplify like this, okay? Right, so just be careful with this one.
Okay.
Okay, thank you, Eugene.
Good morning, doctor. Can you see my screen?
Yeah,
Yeah. I'll be presenting number 5. So it's x is an exponential random variable with a mean of lambda, and given the moment generating functions, the A is we need to write down the characteristic function. So from here is the formula of the characteristic functions, and then sub in the fx, and then integrate it, and then finally we will get the lambda over lambda minus it. Is it okay?
okay, let me see.
Yeah, sure.
Yeah, right. So you basically
Yeah.
treat the I as a constant, and then use the machinery of real integration. So that should ITX. Okay. Then
Okay. Then for B is we need to find the distribution of the Sn using A. So I just changed the here become Sn. So it's this is the formula, and then like n. So finally we can see that this distribution is a gamma with lambda and n. Correct.
right. Yeah, because in the difference between this function and the moment generating function of the gamma is that it
yeah.
So this is basically the gamma. I mean like gamma. So I mean like the CF is basically just t replaced with IT. So this gamma with parameters gamma n. So but then why your xn is equal to that?
My Sn.
Why do you have 2 results here?
Which one? Okay. I think it's this one is wrong already. I think this is the
the gamma.
Final conclusion. I
okay.
forgot to cancel this.
Okay.
Yeah, only this.
Yeah. Okay. So yeah, basically it's just this should be actually quite familiar. We basically just using whatever you learned before, moment generating function of IIDs, random variable. So there's nothing complicated here, because basically your I just becomes your T just becomes the IT. Okay. And this one is a basic result. The sum of NIID exponential is gamma.
Okay, thank you.
Usually. All right. Okay, so we are done with this tutorial. Okay. So yeah, so that concludes this course. I know you are waiting for the notes. Okay, so they are almost done already. please check spectrum later in the evening. Right? They just a few more things I want to write, so they should be ready by evening. Okay. So are there any things you want to ask here? How do you feel about this course? Is it too difficult or is still manageable?